Hi, I'm Antonio Sala, and in this video we are going to discuss how to encode a model of a mass spring system in Matlab and how to simulate it. In previous videos we discussed the modeling of this system and taking equilibrium point as the origin, letting all spring constant and masses being equal, we were able to write these 6 equations that describe the system's dynamics, and as it's linear, we were able to write them in matrix form. This is the normalized matrix form representation. A and B are the matrices in the state equation. Then, regarding the output equation, we can extract whatever magnitudes we consider being relevant in our particular problem. C equal identity, D equal 0 just outputs everything. However, in Matlab, we will only be interested in the positions, so we'll set up different values for matrix C. So let's see now how we encode into Matlab this spring system model. In this line, we just will give 1 kilogram, 1 Newton per meter, and 0.1 friction coefficient, same for all the springs and masses. And we will encode matrices A and B by simply copying from the theoretical developments. As you can see, we just wrote this in here, and this matrix is encoded like this. So this is it, just copying A and B. In this problem, if we don't wish to plot the speeds, we just want the positions, then positions are the first, third, and fifth state variable. So this C matrix extracts that first, third, and fifth state variables, and then the matrix is 0, but okay, as there are 3 outputs and 1 inputs, the dimensions of D must be 3 times 1 in order for this expression to have sense, and matrix C is, of course, 3 times 6. In this way, these operations can be correctly made. So we extracted the positions from these dynamics, and hence we have all the numeric matrices involved in this normalized representation of a linear system. So how can we simulate these differential equations? Well, let's do it. We will present 2 options, one using a generic ode45 simulator, and a second option using the linear simulation command from Control System Toolbox. Of course, in any actual application, we just need to choose either the first or the second one. We are carrying out both of them for the sake of comparison of accuracy and execution time. So how can any simulation be set up? Well, we need to define 2 things. First, initial conditions. Initial values of positions and speeds, of course in this order. I can set them to any value I wish. If I set them to 0 and I have a non-zero input, then that kind of simulation is called forced response. And if I set them to a non-zero value and I set the input to 0, commenting these lines, sort of, then okay, 0 input, non-zero initial conditions receives the name of free response. But anyway, the simulation code is the same. I mean, I need to set input and initial conditions at will, and 0 is as beautiful as any other number as far as Matlab is concerned, even if from an engineering point of view it may have a different meaning. So in the first simulation we are carrying out, I will set just a pure forced response, 0 initial conditions, and sinusoidal input. In a forthcoming video, we'll make more simulations and animations. I will simulate 80 seconds, wishing to get a value of the positions every 0.01 seconds. So these are 8,000 samples. And once I have the simulation time, initial conditions, and input function, recall that the input is the displacement of the rightmost end of this chain of springs. Once I have all that, I can carry out the simulation. Let us first use a generic simulator. What I mean generic, ode45 for instance, is that it can simulate any ordinary differential equations in this form. And it doesn't care whether f is linear or nonlinear. So, which is f in my linear system? This is it, Ax+Bu in matrix form. So, returning to Matlab, the first argument to ode45 must be this function. Second argument to ode45 is the set of times in which I wish to obtain a simulation. x0 is the initial condition. And last, I set relative and absolute tolerances for the solver. And the output is the set of simulation times and the states x at each simulation time step. In this case, this and this are identical. In other setups, depending on the tolerances, this time instance in the ODE solver may be different from capital T. This XODE is the solution, in this case 8,000 samples of 6 states, because it returns the whole state vector. When we execute, we'll see how long it takes to simulate. And if I wish to have only the positions, then I need to either evaluate the output equation multiplying by C matrix, but okay, in this case, as C matrix just extracts the position, I can do it by hand. So XODE is 6-dimensional, and in here I get the 8,000 samples of the 3 positions. Once I have this, I can just plot it. Simulation would be finished. But as the system is linear, the control system toolbox has some specialized code for linear system simulation. In particular, I can introduce into the toolbox normalized state space representation with the SS state space command. So in this sys.spos, it stores these equations in whatever internal form programmers desire, and it prepares whatever it needs for simulations. In particular, the lsim command is linear simulation. I give him this state space representation. I give a set of inputs and the times in which that inputs take place, and in fact this command assumes linear interpolation between the inputs. So this capital U is computed by evaluating this function of time at every of these instances. It's just the way that lsim works, okay? In ode45, I used this function of time, and in lsim, which uses some exponential formulas inside, we need a vector of inputs and a vector of times. Each programmer decides how to interface with the user, and the user interface of ode45 is different from that of lsim. Well, okay, anyway, we give the initial conditions, the input, and the simulation times, and the object with this matrix data inside, and it gives me the positions, and, well, with doc, I can time how much it takes to execute to compare with ode45. I can also compare the solutions, the difference between pos ode and position of lsim. And I will also display the radio of the execution times. And I will plot the two simulations, and I will see that they are coincident. Let's see. So if I run this code, we can see, for instance, that ode45 took 24 milliseconds to run this simulation, 8,000 samples plus the initial condition, and that lsim from the control toolbox took 2.6 milliseconds. So lsim was in the simulation 9 times faster. It seems that on average, the lsim command it's quite faster than ode45 because lsim can use explicit exponential formulas, whereas ode45, as it needs to be valid for nonlinear stuff, needs to do more complicated operations. And the difference between the solutions, well, it's kind of the sum of the squared error is 10 to the minus 8. This is the square root, 10 to the minus 4. And this is the sum of 8,000 samples. So, as we said, the tolerances were 10 to the minus 5, 10 to the minus 6. So, basically, this tells me that solutions are the same. And indeed, if I see these plots in here, we see that I superimposed the two simulations. There should be 6 lines here, but okay, these two simulations are coincident, so only 3 lines can be seen, which are the positions as a function of time which solve this differential equation. In a forthcoming video, we'll see some animations and we'll try to intuitively understand the meaning of all this. In here, we just are discussing, so we'll summarize and conclude. In this video, we are just discussing how to encode the linear system of equations. It's easy, just copying A, B, C, D. And once we define initial conditions and input, we can solve it with a generic solver, such as ode45, or we can simulate the time response with a specialized solver in linear systems, such as lsim. We did both ways here to compare, but of course, in a real setup, I would use ode45 if my system is nonlinear, and lsim if my system is linear. So this is it. Thanks for watching.